In this video, we are going to explain about the project title 3D CNN and autoencoder based gas detection in hyperspectral images. Introduction. Imaging spectroscopy, which has a history of several decades, has been widely used by geologists to identify materials and map minerals. This technology allows the characterization of minerals based on their spectral signatures. Gas leaks, particularly in developed countries, pose a significant environmental problem. They present immediate risks such as explosions and long-term risks like health issues including cancer. Detecting and controlling gas emissions is crucial for environmental protection. The project proposes the use of infrared remote sensing technology, specifically forward-looking infrared hyperspectral cameras, as a solution for monitoring gas emissions from a safe distance. These cameras can capture hyperspectral data to detect and identify gases in the environment. Previous studies in the field have employed statistical detection methods and signal processing operations for gas detection using hyperspectral imaging. These methods involve analyzing the spectral data to identify the presence of specific gases. In gas detection methods, it's common to convert radiance data to luminance temperature values. This conversion, coupled with thresholding operations, helps in the detection of gas emissions in the hyperspectral images. Thresholding involves setting specific criteria to identify the presence of gases based on temperature values. Objective. The primary objective of the project is to identify and quantify harmful gas emissions such as methane and sulfur originating from industrial activities. This detection is crucial for protecting the environment and human health. The project utilizes hyperspectral images collected from drones or satellites. These images provide a wealth of data in the form of spectral signatures which contain information about the gases present in the environment. The project employs a 3D convolutional neural network 3D CNN with an autoencoder architecture. This combination of techniques is used to process hyperspectral data. The 3D CNN can handle the complex 4D data, and the autoencoder extracts essential feature while reducing data dimensionality. The spectral angle mapper SAM distance formula is utilized to measure the spectral similarity between hyperspectral images and a known database of gas spectral signatures. This comparison allows for the detection of gas presence within the images. The project's overarching goal is to enhance the accuracy of gas detection. It achieves this by integrating deep learning techniques such as the 3D CNN and the autoencoder into the analysis of hyperspectral data. These advanced techniques improve the project's ability to identify and quantify harmful gas emissions, contributing to environmental protection. Requirements of the project are: hardware requirements of the project are operating system of Windows, processor of Wi-Fi and above, RAM of 8GB and above, hard disk of 25GB and above. Software requirements of the project are: application is Anaconda, primary language used in the project is Python, front-end framework is Flask, back-end framework is Jupyter Notebook, database is SQLite 3, front-end technologies used in the project are HTML, CSS, JavaScript and Bootstrap 4. Working modules or flow of work. To implement this project, we have designed the following modules. The first module is importing the packages. This module involves importing the necessary Python libraries and packages required for the project. These packages include tools for data manipulation, machine learning, and deep learning, among others. Importing the right packages ensures that the project has access to the needed functionalities. Exploring the dataset. Hyperspectral spectrum images dataset. In this phase, the project examines and familiarizes itself with the hyperspectral spectrum images dataset. This includes understanding the structure of the data, the format of the hyperspectral images, and the available labels or gas emission information. Exploratory data analysis (EDA) may also be conducted to gain insights into the dataset. Data pre-processing. Data pre-processing is a crucial step where the raw data is cleaned, transformed, and made ready for model training. This may involve tasks like handling missing values, normalizing data, and ensuring data quality. For hyperspectral data, pre-processing might include noise reduction and spectral signature extraction. Splitting dataset into train and test. To evaluate the model's performance, the dataset is typically divided into two parts, a training set and a testing set. The training set is used to train the machine learning or deep learning models, while the testing set is used to assess their accuracy and generalization to new unseen data. Building the model. This module focuses on the construction of the gas detection model. In this project, the model is based on a 3D convolutional neural network 3D CNN with an autoencoder architecture. The model's architecture is designed and defined, specifying the layers, activation functions, and other parameters that govern its behavior. Training the model. With the model architecture in place, the project proceeds to train the model using the training dataset. During training, the model learns to recognize patterns in spectral signatures associated with different gas emissions. Training involves multiple iterations, epochs, where the model's parameters are adjusted to minimize prediction errors. Flask framework with SQLite for sign-up and sign-in. This module extends beyond the machine learning aspects and involves setting up a web framework, specifically Flask, with an SQLite database for user management. It allows users to sign up and sign into the system, which might be used for authentication or for accessing the gas detection service. The given input is pre-processed. This step refers to the preparation of the input data received from users. Before input data is passed through the model for gas detection, it needs to undergo pre-processing similar to what the initial dataset underwent. This ensures that the input data is in the right format and quality for the model to work effectively. The trained model is used for predicting the result. After the gas detection model has been trained on the training dataset, it is ready to make predictions on new unseen data. In this module, the trained model is applied to hyperspectral images to predict the presence of different gases. The model uses the knowledge it gained during training to make these predictions. Final outcome is displayed. Once the model has made predictions on the test or validation dataset, the results are displayed or reported. The final outcome may include information about which gases are detected in specific images or areas. It could also provide confidence scores or probability estimates for the presence of gases. In this project has an extension to the primary model, an ensemble model is introduced. Ensemble models combine the predictions of multiple individual models to produce a more robust and accurate result. The ensemble model integrates the outputs of different algorithms such as convolutional neural network CNN, bidirectional models, and gated recurrent units. Algorithms used in the project are CNN, convolutional neural network. CNN is a deep learning algorithm that is particularly effective for image processing tasks. It's widely used in computer vision applications. In the project, CNN is used in the 3D CNN architecture for analyzing hyperspectral images. The 3D CNN is capable of handling the unique structure of hyperspectral data, which includes spectral bands as the first dimension and RGB-like values as the remaining three dimensions. CNN plus BiGRU, convolutional neural network plus bidirectional gated recurrent unit. This is an extension of the CNN model and incorporates recurrent neural network RNN elements, specifically bidirectional gated recurrent unit BiGRU. CNN are excellent for capturing spatial information and data, such as detecting edges, textures, or patterns. However, they may not capture sequential information effectively. Bidirectional GRU, on the other hand, are a type of RNN that can model sequential dependencies in data by processing it in both forward and backward directions. In the context of the project, combining CNN and BiGRU enhances the model's ability to capture both spatial and sequential information from hyperspectral images. This is useful when dealing with data that exhibits both spectral and spatial dependencies. Comparison graph. This is the accuracy comparison graph. On the x-axis, we have the accuracy score, and on the y-axis, we have the algorithm name. And from this graph, we can say that CNN plus BiGRU performs well. Accuracy is a measure of the overall correctness of a classification model. It calculates the ratio of correctly predicted instances, both true positives and true negatives, to the total number of instances. This is the precision comparison graph. On the x-axis, we have the precision score, and on the y-axis, we have the algorithm name. And from this graph, we can say that CNN plus BiGRU performs well. Precision is a metric that assesses the accuracy of positive predictions made by the model. It calculates the ratio of true positives, correctly predicted positive instances, to the total number of positive predictions, true positives plus false positives. This is the FN comparison graph. On the x-axis, we have the FN score, and on the y-axis, we have the algorithm name. And from this graph, we can say that CNN plus BiGRU performs well. The FN score is the harmonic mean of precision and recall. It is a balanced measure that considers both false positives and false negatives. It is calculated as 2 times the product of precision and recall divided by the sum of precision and recall. It provides a single metric that balances precision and recall, making it useful when we want to consider both false positives and false negatives in the evaluation. This is the recall comparison graph. On the x-axis, we have the recall score, and on the y-axis, we have the algorithm name. And from this graph, we can see that CNN plus BiGRU performs well. Recall, also known as sensitivity or true positive rate, measures the model's ability to correctly identify all relevant instances in the dataset. It calculates the ratio of true positives to the total number of actual positive instances, true positives plus false negatives. Execution. To execute this project, first we need to open the code folder which contains the project source code files. This is the code folder. This is the static folder. This folder consists of files related to CSS, JavaScript and Bootstrap. This is the templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html and more, which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. This is model file, which contains algorithm information which will be loaded into the project code during runtime. This is notebook file. This Jupyter notebook file contains a combination of code, graphs and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. This is signup.db file. This file is the database file used to store user information. First, we need to copy the path of the code folder from the address bar of the file explorer. So I'm copying the path. Open the Anaconda prompt. Use the cd command followed by a space and paste the copied path and hit enter. This command is used to change the current directory to the code folder's path. Compile the app.py file using the command python space app.py. So here I'm typing python space app.py and hit enter. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address. Localhost, which is this, and port, which is this. Now copy this local link provided by the Flask framework. I'm copying the link and paste this copied link into any web browser. I usually prefer Google Chrome and hit enter. The home page image of the project is displayed in the browser. This is the front end built using Flask framework. If we are a new user, click on log on. Here we need to enter all these details to register. But I have already registered, so click on sign in. So here we need to enter the username and the password which we have created, and then click on sign in button. So we have logged in successfully. So here we need to enter all these parameters. These parameters are the key variables or values used for data processing, feature extraction, model configuration or evaluation within the deep learning based gas detection system. These parameters play a crucial role in the functioning and performance assessment of the model. Parameters like x1, x2 till x11 may be undisclosed in research projects to protect intellectual property, address privacy concerns, manage complexity, and compile with publication guidelines. So here I am entering these parameters value now. So here I have entered all these parameters from x1 till x11. Now click on predict. So here we got the result, methane based gas detected. Now we will enter another set of parameters. So I'm entering another set of parameters now. So here I have entered another set of parameters. Now click on predict. So here we got the result, sulfur based gas detected. Now click on sign out. The conclusion of the project is, the primary goal of the project is to address environmental pollution by identifying and quantifying gas emissions from industrial sectors. Industrial gas emissions can harm the environment, and this project focuses to help combat such pollution. The project leverages hyperspectral images captured from industrial gas leakage scenarios. It employs the spectral angle mapper (SAM) distance formula, which calculates the spectral similarity between these images and a database of known gas spectral signatures. This approach enables the detection of different gas emissions present in the image. The project created its dataset, including gas labels, for training the 3D CNN model. Additionally, the project utilizes external datasets related to methane and sulfur gas leaks for training. This combination of data sources enhances the model's ability to recognize various gas emissions. The project demonstrates the effectiveness of deep learning techniques, particularly the 3D CNN with an autoencoder for gas detection in hyperspectral images. This application of advanced machine learning and neural network models underscores the potential of these technologies in addressing environmental protection concerns. The project's primary contribution is its role in reducing environmental pollution. By identifying and quantifying gas emissions in industrial sectors, it aids in environmental protection efforts. It provides a valuable tool for monitoring and controlling gas emissions, helping to mitigate the harmful impact of pollution on the environment.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.